Yeah.
Hey Paco, how's it going?
Well enough.
Well enough.
Well, I'm gonna get my second shot on Thursday, so yeah.
Oh yeah, cool. Nice.
Yeah.
Very
How
nice.
about, how about you?
It's going all right. Just kind of over the semester, you know.
I know, right? Ah,
Yeah, especially it's just the grading of my classes is getting to me. That's like the worst part in my opinion.
oh yeah.
Yeah, like sometimes I don't even know if they even read the comments I leave them on their quizzes and stuff.
Oh yeah. They don't. I can tell that there are some who don't because I do some grading
Mm.
also, but yeah, you can tell the ones who don't read.
Yeah, they just make the same mistakes. What are you grading for?
3200.
Oh, cool. Cool. How's it going, Freddie?
It's going pretty well. Computer's being kind of slow, but it's fine.
Oh, it's time for
Lagging a bit.
refresh.
Yeah, probably.
Yeah.
Let me check something.
I got my second jab this weekend.
Nice.
Oh, how do you feel?
I felt awful
Oh
this
God.
weekend. Like,
I'm gonna get mine on Thursday.
oh yeah, nice. Yeah, I mean, I had like a fever and really bad chills and like the worst headache and just body aches, but I'm feeling mostly better now. So
Oh, good to hear.
Nice.
Mhm.
So you're giving a talk tomorrow, huh?
that's right.
The Mora curves, very nice.
Yeah.
Yeah, I think Mancelos at some point was like, you should give it to, yeah, he's giving me a thumbs up. So
Yes, I requested. Yes.
cool.
Thank you for this. Actually, it's one of the things you're planning to start at some point, but you never have the time or you're never in the mood, right?
Yeah. If there's anything in particular you want me to hit on, let me know. It's gonna be like almost completely expository.
That's what I want. I know nothing about him, so.
Okay, cool.
So are you done, Makoto? Did you submit your final version of the thesis?
Nope, Dino still sends me a correction, so I'm gonna be submitting in the last minute, I'm guessing.
I see. So when you submit this, you need to email Laura and let her know because they cannot approve it unless Laura has told them to. Like they need to see that your advisors are okay with your thesis, basically.
Well, I think Dino jumped the gun ahead, and then I think Neil already approved it, but I don't think I should have approved it because I think you approved my draft, not the actual final version.
Oh, I see. So you're saying, I see. But I think you first need to submit this, though, right?
Well, I think that he approved my draft, I imagine. Because it gets them in the same place, right? Submit the draft and the final copy at the same place. So.
Yes, but they don't check the draft. They once you submit the final version, then they need to check this.
Yeah, I'm just saying that I think Dina's like jumped the gun somewhere and then just like told everyone to like approve it or something.
I see.
Yeah.
I see. But yes, I mean, when you submit this, just make sure you send an email to Laura to make sure that everything will be okay. Because I submitted this last week, and I waited for like 7 days and nothing happened. Yeah. And it was still under review. And then I told this to Laura, and within 1 hour it was fixed. So you need to just send, I guess, an email to grad school.
Yep.
And I'm finally done. So.
Mm-hmm.
So that means you will be busy for the next week, right, or so?
Yeah, I mean, I thought I was done, but like, turns out that's not the case. So, what can you do?
I think I'm getting my second shot on Thursday, and then I'm ready to get back to life. You know, I'm sick of.
I mean, what are you gonna do in Athens though? Like, I don't know.
Well, you know, I wasn't an extreme person even before, right? But you know, even just going for a walk downtown, right? or getting a beer.
I see. Yeah.
I'm not sure though if I still feel safe to go to get a beer on you know, or get some food like in a space, like, you know,
in a restaurant or like a bar or something.
Yes.
Yeah.
If it ends right, probably yes, but otherwise.
So sorry, I'm a little late, just trying to get some references in the notes. Yeah, any questions? No? Okay, so business as usual. I will see if this is too ambitious, but I mean to finish the Lubin-Tate approach to local class field theory today, so that should be exciting. Let's get into it. Okay, so yeah, so the next thing that we want to do, so we've talked about the Lubin-Tate class field theory generates this, what is this? This extension K pi. That's the extension obtained by adjoining all these torsion elements in our Lubin-Tate formal R module. And so we saw that that generates an abelian extension. It's totally ramified. The Galois group is the unit group of the local field. And so what we're trying to show is that in fact is a maximal totally ramified abelian extension, which means that when you take the compositum of that abelian totally ramified extension K pi with the maximal unramified extension, we should get the maximal abelian extension. Okay, and then we just want to do this. We also just want to connect this with our previous formalism involving the reciprocity map, and so let's do that. Okay, so this is just a totally innocuous lemma. I have a complete discrete valuation field K. I have an algebraic extension E of K. And suppose I have an element in the completion of E that is separable algebraic over E, then it is already in E. Okay, so if you're in the completion and you're separable algebraic, then you should already be in the field. Okay. Yeah. Okay, so this is not such a big deal. So let's see. Right. So if we have a Galois extension even of infinite degree, then the automorphism group acts continuously on L. So this is just a basic fact about complete discrete valuation fields. All right, and so the way you show this, for instance, is by reducing to the case where the degree is finite. Sort of every Galois automorphism is kind of locally finite in the sense that it has finite orbits, so you can reduce to that case. And now we're just looking at k-linear endomorphisms of a finite dimensional k vector space, and of course they're going to be continuous. So that's not much content there. Okay, so for this, unusually for me, I'm going to write E bar for the topological closure of E in the separable algebraic closure. Okay, and so then it's enough to show that E bar is equal to E, because I mean that's really kind of exactly what I want to show, because then what's going on here? So then I have an element in the completion which is separable algebraic, and so what are we saying here? Let's see. So therefore, if it lies in the completion, then then E is dense in its completion, so it should be inside the. Anyway, sorry. If we just let me stop for a second and try to say this again. So. Yeah, so if everything which is, so I take the closure of E in the separable algebraic closure, if every such element is already in E, and then I take an element in the completion, which is separable algebraic, well, then it's in E sep because it's separable algebraic, and E is dense in the completion, and so therefore it must lie in the closure. Okay. Every element of the completion of E is the limit of a sequence in E. Okay, so it's enough to show that E bar is equal to E. And so if I have an automorphism of the separable closure, then it acts continuously on E sep. We just said that. So since it fixes E pointwise and it's continuous, it also fixes the closure of E pointwise, and then you just apply Galois theory. So then by Galois theory, this E bar is some kind of separable extension. So of E, so it's going to be obtained from the separable closure by, it's the fixed field of its fixed subgroup. This is just Galois theory here, but we just said that everything that fixes E bar pointwise is the same as that if you fix E pointwise, you fix E bar pointwise. So these two subgroups are the same, and so I can replace this with this, and then the fixed field of that is E. Okay, so just by Galois theory, we get that E bar is equal to E. Okay, so there's not too much to that. I guess out of the side of my mouth, I kind of wonder. So there's this word separable in here. Is this actually necessary? So I don't know off the top of my head, but you could ask whether if you had an element in the completion that was algebraic but not separable, shouldn't it still be? But okay, we don't need that, so we'll just move on. So yeah, the next result here, this is certainly an important result. So I'm constructing an abelian extension, some abelian extensions of K. The Lubin-Tate extension definitely does depend on the choice of uniformizer, as we sort of talked about. But then if I take the compositum with the maximal and ramified extension, I would like L pi and L omega to be equal to each other because I want them both to be the maximal abelian extension of K. So if that has any chance of being true, they should certainly be equal to each other. Okay, so that's kind of a stepping stone to that. Okay, and so again, the lack of uniqueness of this Lubin-Tate extension, once you take the compositum with the maximal unramified extension, they should become equal. Okay. So let's see. I think this is just a quick consequence of the lemma. So all right, you take little f in f pi, you take little g in f omega, and by our previous result, remember even when you switch uniformizers, the Lubin-Tate formal group laws are isomorphic, not over R, but over the completion of the unramified extension of R, that's R infinity. So in particular, that they're isomorphic over that ring, they're isomorphic over the fraction field of that ring. Okay. And so, so what does that tell us? That tells us, so if the formal group laws are isomorphic formal group laws are going to generate the same torsion point fields. So again, we talked about that as well. That's like some kind of formal or local analog of the fact that isomorphic abelian varieties or commutative algebraic groups are going to generate the same torsion point fields. And so since they're isomorphic over K infinity, then if you take the torsion point fields and take the compositum with K infinity, then you should get the same torsion point fields. Okay. So this is like saying if you have two abelian varieties and they're not isomorphic over the ground field, but they're isomorphic over some extension of the ground field, their torsion point fields don't have to be isomorphic as extensions of the ground field, but after you make the extension under which they become isomorphic, then over that larger base, the torsion point fields become not just isomorphic, but equal. Okay, and so you think about this for a second, and then you say this is more than enough to imply that the completion of this composite extension is equal to the completion of the other. How do you see this? You just see they're both complete, and you just see that one lives inside the other. So because of this, so the completion, so L pi is K pi K on RAM, and so you see from this that K pi K on RAM is definitely living inside L omega, right? Because of this equality, and so therefore each one is living inside the. Wait, maybe I'm not saying this quite right. Let me think for a second. Yeah, so you have so K infinity is the completion of the maximal unramified extension. Okay. And so if I want to believe that that L pi is inside here, I just need to believe, so L omega, I have K on RAM inside of L omega, and I have let's see. Yeah, no, this is giving it to me, right? Because K infinity K pi is equal to this, and this one is living inside of the completion. Okay, so the two completions, excuse me, are isomorphic to each other. And then if you just apply the lemma, so what did the lemma say? The lemma said that if I had an algebraic extension of a complete discrete valued field, and then I had anything that was separable algebraic over the completion was already in the field. And so this, if you apply the lemma here, then yeah, so I mean L pi and LW are both separable algebraic extensions of K, and so the lemma is going to imply that they are equal to each other. Okay, so just a little, I mean, all we're doing, so all of this is just mild fussing about the distinction between the maximal unramified extension, which is not complete, and its completion. Okay, and so for some of the things we have to do, we kind of have to be working over a complete field to define the one variable formal power series that gave us the isomorphism. That had to be over the completion, but then you know, whenever we're doing something kind of more algebraic, you know, a formal power series is not a finite object because it has infinitely many coefficients. And so it's actually kind of, I haven't really thought about it deeply, but it's plausible that if you sort of pick a bad little f, then you really might have to go over the completion of the maximal unramified extension in order to define the isomorphism. But now we're working with algebraic extensions. They should be much more rigid. And anyway, so we're just kind of going up to the completion of the maximal unramified extension, making a mild valued fields argument, and then coming back down. Okay, so now we know that this extension is independent of the choice of uniformizer. So what do we know about this? I guess this is probably what's coming on the next page, but we know that either any one of these, eventually I'm just going to, in fact, maybe now is a good time. If they're equal, how about I just call them L? Okay. So this L is an abelian extension of K. The Galois group is isomorphic to the unit group of K. So U or R cross, that's the Galois group of the totally ramified extension. We proved before, cross the Galois group of the maximal unramified extension, which is Z hat. Okay. And so if you remember, we're trying to show that the Galois group of the maximal abelian extension of K is R star cross Z hat. So that doesn't prove it yet, but we're definitely zeroing in on the fact that this L is actually the maximal abelian extension. Okay. So the next thing to do is to establish compatibility with the reciprocity map, right? Because our class field theory formalism was involving the reciprocity map. Okay. So I have this L pi, which is okay, but again, I can just call it L if I want to, but maybe to establish some things, it's helpful to call it L pi. And so now by theta, I'm just going to here, this is going to be the reciprocity map. Remember, the reciprocity map was first defined for any finite abelian extension and gave an isomorphism from the norm co-kernel to the automorphism group of the abelian extension. But then by passing to inverse limits on the right-hand side, you can define the reciprocity map for any abelian extension. And so that's what we're doing. Okay, so we're just defining this sort of infinite level on the right-hand side reciprocity map by passing to the limit over the finite abelian extensions of L pi over K. Again, secretly, L pi is supposed to be the maximal abelian extension. We don't know that yet. And so what's happening here? And this is really just a compatibility of what we've done with the reciprocity map. So the claim is, if you take the reciprocity map and you apply it to pi, the uniformizer, then you get some automorphism, right? And so the claim is that K pi is the fixed field of that automorphism. Okay. And then, so this theta pi, so what are we saying? We're saying that theta pi acts pointwise fixes L pi, and L pi, pointwise fixes K pi, and in fact, K pi is the maximal extension on which theta of pi pointwise fixes. That's what the first thing is saying. And so this is telling, in particular, this is telling us how theta of pi is acting on k of pi. L pi is the composite of these two fields. So if I tell you, if I want to define an automorphism on the two fields, especially since they're disjoint, it's enough to tell you what the automorphism does on k pi. I just did. And it's enough to tell you what the automorphism does on the maximal unramified extension. And the claim is it should just induce the Frobenius automorphism, the one that reduces modulo the maximal ideal to x goes to x to the q. Okay. So again, we know that k pi and k on RAM are linearly disjoint over k. And so then the automorphism group is going to be the direct product of the two. Okay. Right, well, I think we knew that last part already because k on RAM is unramified and k pi is totally ramified. So, okay. So we have to prove just the first part. Okay. So we have this just usual Galois theory short exact sequence. So I have the automorphism of the entire extension. Yeah, this short exact sequence is just coming from the automorphism groups of the tower here. Okay. And so let's see. Oh, I guess, well, all right. I also have a k on RAM. Okay, so that's the picture. All right. And so H looks like H is this one. Okay. And then this one, this k on RAM over k is topologically cyclic generated by the Frobenius. Okay. So that's we have such a short exact sequence of profinite groups. And then what is this? This is what I was a little bit late just filling in the reference. This is just this result that says that, I'll show you the diagram, that if we go from one finite abelian extension to another, then the reciprocity map is compatible with restriction on both sides. Honor compels me to admit that this is the result, but the proof in Harari seemed not quite complete, but no big deal. Yeah, so this is this one. If you have two finite Galois extensions, you have a natural inverse system on the co-kernels of the norms. You have a really natural inverse system on the abelianized automorphism groups. You have reciprocity maps on both sides. And so it's just the commutativity of this diagram. Okay. So in other words, if you take the reciprocity map as an automorphism, now this is true for Galois extensions. If we abelianize, our extensions are abelian now. So if you take the reciprocity map for a bigger abelian extension and you just restrict it to acting on a smaller field, then you're going to get the reciprocity map on the smaller abelian extension. Okay, so the reciprocity map is compatible with restriction. Okay, so because of that, well, what does that mean? The reciprocity map is compatible with restriction. So if you restrict theta pi to the maximal unramified extension, then we get the Frobenius map. Okay, maybe that was probably another result too. So let me press my luck and flip back and see if I can find that. Brouwer groups. Yeah, here it is. So if you have a unramified extension, then the reciprocity map on an unramified extension is really easy. It's just given by the right power of the Frobenius to the valuation of that map. And so of course, if it's a uniformizer, then you just get Frobenius. Okay, so that was a lemma. You can't see this, but it's lecture 17, page 6. So I think I mean both of those things. Okay, so this thing, therefore, it's a lift of the Frobenius map. Okay, you restrict it down to the maximum ramified extension, and you get the Frobenius map. So, and then this is the same thing that we've seen before. This is a free profinite group, so the sequence is automatically going to split, but we're getting a canonical splitting here. Okay, so that's the point. This automorphism is splitting as the product of H. So these are the extensions which are acting trivially. on the maximal unramified extension. And yeah, so that's the point. So this theta of pi is giving me a lift of the Frobenius here. That's what's happening. We're getting a canonical lift of the Frobenius. And so by definition, I sub pi is just this, we take this one automorphism, we take the subgroup generated by it, we close it. It must be, it maps down to, this automorphism maps down to the Frobenius, and so therefore the subgroup, therefore this I pi must be isomorphic to z hat as well. It's got to be isomorphic to a quotient of z hat, and under a quotient it's still z hat. Okay. And so now, yeah, this is really just a little Galois theory is pretty much what's happening here. So I take my k pi to be k prime, excuse me, to be the fixed field of theta of pi. And so if you're tracking it, I want k pi to be k prime. That's what I'm trying to show. Yeah, that's mostly that's pretty much what I'm trying to show. I did show that, I just showed that theta pi induces the Frobenius on Kn Ram. That was here. And so the only thing that I really have left to prove is that k pi is the fixed field under theta of pi. So okay, let's just prove this using Galois theory. So let's call the fixed field under L pi something, okay? And then again, just this short exact sequence is telling us that L pi is going to be the compositum of the unramified extension together with the fixed field of something. Okay, so this is the field theoretic analog of this group theoretic statement that the automorphism group is the direct product of H and I sub pi. Okay, right, because k prime is the fixed field of I sub pi, and k on Ram is the fixed field of H. Okay, just Galois theory. All right, so for all positive integers, if I take the map, this finite level reciprocity map, okay, well, the way the reciprocity map works is it's trivial. The kernel of the reciprocity map is precisely the image of the norm, right? We established that some time ago. And we just proved in the last lecture that pi is a norm from this, this totally ramified Lubin-Tate extension. And so you put those two things together and you see that the reciprocity map at every finite level is trivial on pi. And so if it's trivial at every finite level, then it's trivial in the inverse limit. Okay, so this, okay, here, what was this corollary? This was the same thing I flipped to before, just the reciprocity map is compatible with these inverse systems. So if you know that the reciprocity map is trivial at each finite subextension, then it's trivial on the whole thing. Okay, so theta of pi restricted to k pi is equal to 1. Remember, k prime was precisely the largest field on which theta of pi acts as the identity. Well, k pi, that's a pi. I don't know why it doesn't come up as clearly on the screen. K pi is one subfield on which theta of pi acts trivially, so therefore it must be a subfield of the field on which theta pi acts trivially. Okay, so that gives me, I'm trying to show that k pi is equal to k prime, and I'm almost done. I just hit it with a little bit more Galois theory. So let's let H prime be the automorphism group of L pi over k pi. And so again, I pi is should be a subgroup of that, because I pi is generated by theta of pi. And so as we just said, that theta of pi acts trivially on k pi. And so fine. So therefore, I pi is a subgroup of that group H prime. And then again, Galois theoretically, we know that L pi is equal to, this is not even good, this is just by definition, we know that L pi is equal to k on Ram times k pi. And so what are we getting from this? This is telling us that that H and H prime are disjoint subgroups. Their intersection is equal to 1. So yeah, so why is that? Let's see. So H was the ones that fix, H are the automorphisms that pointwise fix K on Ram. H prime are the automorphisms that pointwise fix K k pi. Well, because they're linearly disjoint, their intersection is k. So let's see, that's not the right one. Because their compositum is such a guy, if it were in the intersection, it would fix k unrammed pointwise, and it would fix k pi pointwise. Therefore, it would pointwise fix the entire extension, and therefore it's trivial. Okay, so it's really just Galois theory. So what do we get from this? We get from this that the automorphism of L pi over k must be h times I pi. Okay, so again, why is that? Let's see. So what was I pi? I pi was this guy, which is mapping down there, and h prime was that one. Okay, and so we know that h and I prime are disjoint because I pi is inside h prime, and we just said that they're disjoint, and together they should generate the entire automorphism group. Okay. Just think for, again, one more second here. So H, sure. Yeah, no, again, the fact that this group is the direct product of this, again, is on the Galois side for saying L pi is the compositum of these two linearly disjoint extensions. Okay, so one field is the compositum of two linearly disjoint extensions if and only if the Galois group is the direct product of the Galois groups of the two extensions. So okay, so again, we have that just by Galois theory. And so now, yeah, so what's going on? We know that the automorphism group is equal to h times I pi. We know that I pi is contained inside of h prime, right? And so let's see what's happening here. What's happening here is, let's see, h prime. H prime is the automorphism group over k pi. Okay, right. And so H prime and H. Okay. Yeah, so what I think what we got here is that the Galois group was equal to H cross I pi. It's also equal to H cross H prime. Okay. And H prime and I pi is contained inside of H prime. And so, you know, if your group is the direct product of two subgroups, and that's also the direct product of two groups where the first one is a subgroup of the first one. So yeah, let me draw something here. So I have aught of L pi over k is equal to, on the one hand, H cross I pi, but it's also in here, I have, nope. In here, I have H cross H prime, but I also have an equality here. Okay, so the only way that can happen is that if this is actually an equality, and so therefore H prime is equal to I pi. Okay, and so what does it mean that H prime is equal to is equal to I pi? Again, just by Galois theory, H prime was the fixed field of k pi, and H prime was the fixed field of k prime. Okay, and so I think I'm saying it the wrong way around. Let me try that one more time. So those fields are the same. Sorry. So yeah, one more time. K pi is the fixed field of H prime, and K prime is the fixed field of I pi. And so since H prime and I pi are equal to each other, that means that K prime is equal to K pi. Okay, so hey, it's really just Galois theory is all that's happening here. But that's what we wanted to show, because now really the content here is that K pi is precisely the fixed field under the reciprocity map applied to the uniformizer pi. Okay. All right. so now, yeah, this is a very important result. Okay, this one is kind of the explicit part of the explicit local class field theory. So we have a local field, we have a uniformizer pi, we have a one variable form of power series F, same as usual. We have our L pi, which is, again, we're going to show very soon that this is the maximal abelian extension. And now I'm going to define a map R pi. And the idea is this map R pi is going to be pretty explicitly described using Lubin-Tate stuff. But then on the other hand, what we're going to show is that R pi is the reciprocity map omega. And therefore, we're getting a very explicit description of the reciprocity map on L pi, which the very next thing we're going to prove, I think, is that L pi is the maximal abelian extension of K, anyway, very soon. And so this is going to give us a very explicit description of the reciprocity map. Okay, so how am I defining R pi? I'm defining R pi. It's a map on K star. So I'm fixing my uniformizer. So it would be, it's a group homomorphism. And so if I tell you what it is on pi and I tell you what it is on a unit, then that will determine it as a group homomorphism. So R pi of pi should pointwise fix the totally ramified guy and act as Frobenius on the unramified guy. That's what the reciprocity map applied to pi should do. And then more interestingly, if you're in the unit group, then R pi of a unit should fix K on ram. That's kind of the opposite. But what does it do on K pi? Well, it does the Lubin-Tate thing. So remember, we already have this isomorphism from the automorphism group of K pi over K to the unit group of R. And so if you, that's how it's acting. It's acting as, it's almost acting as the automorphism of K pi that corresponds to the unit U. However, so this inverse is just the inverse function to take us back from R pi into the automorphism group, but then there's another inverse here, so it acts as the reciprocal of U. So if I gave you more time, you might guess that R pi of U acts as theta inverse of U, and it's not quite that. There's an inverse in there. Okay. And so what do we get from this? We get in particular that R pi is independent of the choice of the uniformizer and coincides with the reciprocity map. In fact, we show that it follows that it coincides with the, okay, we are going to show that it's independent of the choice of the uniformizer. That's going to be the first assertion. Yeah, all of this is just the definition of R pi. Okay. Fine, yeah. Okay, so, right, so it turns out that R pi is independent of the choice of pi and coincides with the reciprocity map. Okay, so let's prove this. So first step, well, if I want to show that it's independent of the choice of pi, let's choose a different uniformizer. So let's choose omega, which is a unit times our first uniformizer. And then I'm trying to show that R pi of omega is equal to R pi of pi. Okay. And so, well, there's two steps. You see how it's defined. It acts on the maximal unramified extension in a very simple way. Okay, so R pi of omega, if you restrict it to the maximal unramified extension, well, omega is equal to U times pi. This is a homomorphism, so it's R pi of U restricted times R pi of pi restricted. R pi of U restricted to the maximal unramified extension is trivial. Okay. And R pi pi restricted to the maximal unramified extension is the Frobenius. Okay, and so that was the easy part. We changed by a unit, and the map just doesn't do anything. The map applied to a unit doesn't do anything to the maximal unramified extension anyway. So R pi of omega restricted to K on ram, first of all, is equal to R pi of pi restricted to K on ram, which is half of what we need to show that R pi of omega is equal to R pi of pi, but we're going to use later that it's equal, but it's equal. They're both equal to the Frobenius map. Okay, so the crux of the matter is to show that R pi of omega restricted to K omega is equal to 1. Okay, so that's what we're going to show, right? And so if we, because again, we know that we know that L pi is equal to L omega. And so, so therefore L pi is the compositum of the maximal unramified extension times K omega. All right. So by definition, what was K omega anyway? K omega was obtained by adjoining the torsion points on a Lubin-Tate formal group law associated to a one variable power series little g. Okay, and so then we had, from this previous proposition, we had a one variable formal power series phi with coefficients in the completion of the maximal unramified extension. What did phi do? Phi really did give an isomorphism from capital F sub little f to capital F sub little g over that maximal unramified extension. And so therefore, since I have an isomorphism, then every element in every torsion point for the one formal group is equal to the is some other torsion point under the isomorphism. So I'm just using that I have this isomorphism, and then once I plug in the R infinity points, then I get, you know, honest R modules, and phi is an isomorphism of R modules defined over R infinity. And so yeah, and so therefore I can get from my one uniformizer to another as long as I deal with this formal group law phi, which has coefficients in the completion of the maximal unramified extension. Okay, so let's let S be R pi of omega. That's the thing that we're looking at. So I'm trying to show that S restricted to K omega is equal to 1. And so, all right, well, K omega was generated over K by these elements lambda. So really what I want to show is that S fixes every element of lambda. And again, I'm going to do this by relating the sort of G torsion points to the F torsion points. Okay, so I want to check that S of phi of mu is equal to phi of mu for all mu, which are a torsion point for the other formal group law. Okay. And so luckily we've prepared for this. So we know that S restricted to the maximal unramified extension of K is equal to the Frobenius, right? We were just talking about that, right? Because S is, that's exactly what we just saw here. S restricted to the maximal unramified extension is the Frobenius. There it is. That's S. Okay, right, and so then, so I have this power series, which is not necessarily K-rational, it's defined over the completion of the maximal unramified extension. So I hit it with this, this Galois automorphism, okay, but again, how is it acting? It's acting as sigma. Sigma is the unique continuous extension of Frobenius to K infinity, okay? And then it's part of this result where the phi was defined. So I'm not going to flip back because it's just going to tell you exactly this, that whatever this isomorphism defined over R infinity was, when you hit it with the continuous extension of Frobenius, then it acts as phi composed with U of F. Okay, where again U is what takes pi to omega. Okay, right. So that's a very important piece of information, and then I think it's just a calculation from this point. Okay. So on the other hand, if I take phi mu and I hit it with S, well, what is that? If you just think about that for a second, I should be hitting everything with S. I should be applying S to the coefficients, and I should be applying S to the element mu, right? So that's S phi. Evaluated at SU. Okay, and so SU is going to be given by U inverse of F evaluated at mu. Why? Because mu was, by definition, was an arbitrary torsion point for this formal group law. And that was exactly what we just said. We said that the way that R pi of U acts on acts on K pi is via U inverse, basically. So that's what we're getting there. Okay. Yeah, so that's coming from what I just said. And then now you see why we put the U inverse in here, because somehow there was an extra U that came out of this, and then these cancel, and we get phi of mu. Okay. So what did I show? I showed that S applied to phi of mu is equal to phi of mu, and that's what I wanted to show, if you'll recall. So I was trying to show that S of lambda is equal to lambda, but lambda was phi of mu, so I was trying to show that S of phi of mu is equal to phi of mu. Okay, so what did I just do? I just showed that R pi of omega restricted to K omega is equal to 1. Okay, so right. So now that's what I proved, and now I also know that L pi is equal to L omega. We proved that shortly before. And so then the reciprocity map has the following property. This is what we just saw. The reciprocity map induces the Frobenius on the reciprocity map attached to the uniformizer omega induces the Frobenius on K and RAM and acts trivially on K omega. Okay. And so what's the point? The point is that's what theta of omega does. And we just proved that that's what R pi of omega does. Okay. So R pi of omega is equal to theta of omega. And so what did we just prove? We proved I want R pi to be equal to the reciprocity map. And I just proved that for any uniformizer, not just the fixed uniformizer that I used to sort of build the whole thing up, but for any old uniformizer at all, then the reciprocity map evaluated that uniformizer is equal to my map that this R pi, which is cooked up using the choice of uniformizer and using all the Lubin-Tate stuff, okay? So the right-hand side, it really looks like it depends on the uniformizer, but we showed that it kind of doesn't. And then it's equal to the reciprocity map when you evaluated any uniformizer. And then the last step is really easy. If you consider the subgroup of K star generated by all the uniformizers, it's got to be the whole thing, because K star is generated by any fixed uniformizer times together with all the units. But every unit is a ratio of two uniformizers. So if if two homomorphisms agree on all uniformizers, they agree on all ratios of uniformizers, the group homomorphisms. So they agree on all units. So they agree. Okay, so no problem. K star is the subgroup generated by all the uniformizers, and therefore it really is true that R pi is equal to, really R pi is equal to theta. It's just equal to the reciprocity map, and well, okay, and therefore if that's true for pi, it's true for omega as well. Okay, so that was one of the key steps. So and again, the way to think about this, or at least the way that I think about this, is the R pi is a very, very explicit description of the map. It's just telling you what the map is, and well, it's telling you what the map is on every uniformizer, which is fine, right? As we said. No, it's telling you the uniformizer is telling you what it's doing on a unit. So on the distinguished uniformizer pi, viewing it as R pi, it's no problem. It acts as the Frobenius. And then when you evaluate it on a unit, it acts much more interestingly, but it acts using the it acts the way that U acts on the Lubin-Tate, on the corresponding Lubin-Tate module. Okay. So this is really giving you a very, very explicit description of the reciprocity map on L pi over K. But all right, we're just about ready to prove that L pi is the maximal abelian extension of K. Okay, so fine. All right, so let's. I think I'm going to go a little over today because I want to finish this, or at least get as far as I can. Okay, so next proposition. So, okay, now again, I'm going to do what I said. I did it before, but I didn't use it. So now L will be, I know that L pi is equal to L omega, so let's just call it L. Okay, and this is really the key. This is not the last result, but everything is easy from this. So I have a local field. This really is the existence theorem, right? So what was the last? I kind of did everything from the class field theoretic formalism except for one thing. What was the one thing? I didn't know that I had enough abelian extensions so that every open finite index subgroup of the unit group K star was the norm of an abelian extension. That was the hard part. And this is what I'm claiming. So I'm claiming if you give me an open finite index subgroup H of the unit group, then it is a norm subgroup. Okay, so even this, if you remember what we did before, establishes local class field theory. The fact that every open finite index subgroup is a norm subgroup means that the reciprocity map is injective and therefore induces an isomorphism from the profinite completion of K star to the abelian Galois group of K. But we're getting more because I'm not just saying that it's the norm of any old finite abelian extension of K. I'm telling you it's the norm of a finite degree subextension of L, where L is my Lubin-Tate extension. Okay? And again, just as soon as we get another page, it's going to follow in a few lines from this that L has to be the maximal abelian extension of K. Okay, so let's prove this. The proof is very nice. So the higher unit groups for like the 20th time, this is what they are. And you stare at these and you say, oh, these are the balls around 1 in the local field. So they evidently form a neighborhood basis at 1 in K star. Okay. I guess, well, they form a neighborhood base when you get close enough to 1 they form a neighborhood base of 1 in K. Never mind. Okay. I'm saying things I don't need to say. There are no these do form a neighborhood base of the identity. Okay. So because they form a neighborhood base of the identity, therefore every open subgroup has to contain one of them. That's how neighborhood bases work. Okay, so on the one hand, my finite index open subgroup, just by virtue of being an open subgroup at all, must contain one of these higher unit groups. Again, these are just the balls around 1. Okay. On the other hand, since the index is finite, consider again, play that game, fix a uniformizer pi. Well, if H has finite index in K star, then K star mod H is finite. And so evidently pi has finite order in this finite commutative multiplicative group. What does that mean? It means that some power of pi is trivial in this finite group, of course, because it's finite. And that means that some power of pi, some positive power of pi lies in H. Okay, so that's just group theory. So what did that show us? So by virtue of being open, H contained one of the higher unit groups, U, K, N. By virtue of being finite index, K, H contains some power of the uniformizer. Well, therefore it contains both. And so by definition, VMN is going to be the subgroup generated by the nth unit group and by pi to the m. You think about this for a second. This is definitely an open finite index subgroup in K star. Okay. All right. And so if you think about it, really the crux of the matter is if I can show that this is the norm of a subextension of L, then I'm going to be good. And that's what I'm going to do. So let me let Km be the degree m unramified extension of K. Okay. And then let me let E of Mn be the level n Lubin-Tate guys. This is a totally ramified guy. And let Km be the unramified guy. Okay, and so evidently this is a finite degree subextension of L. L is the maximal unramified, so Km is a finite degree subextension of the unramified piece. And K pi to the n is a finite degree subextension of K pi. So like these are a very, very natural family of finite degree subextensions of L, such that evidently if you union over all m and n, you are going to get L. Right? Every unramified extension. The Km ram is the union of the Km's, and K pi is the union of the K pi n's. And so this is a cofinal system every finite extension of L is contained in one of these EMNs. Okay. And so what am I going to show when I flip the page? Presumably, I'm going to show that the norm of EMN is precisely VMN. Okay, so that'll tell me that VMN is a norm subgroup, and this is a bigger subgroup. So I'll remind you that we already proved that any group which is bigger than a norm subgroup is a norm subgroup from a smaller extension. Okay. How are we going to prove that? Well, we're going to use what we've already established. So if I take U to be a unit and A to be an element of Z, so an arbitrary element of K star is U times pi to the A. And so what do we know? We know that if we take the reciprocity map attached to the extension EMNK over K, so this thing, therefore, what is this thing? This thing takes values in K star and lands in the automorphism group of EMN over K, that finite degree abelian extension. And so, yeah, we talked about this. And so therefore, what is this thing going to do? This thing is going to act kind of as the level n character evaluated at U inverse on K pi of n, and it's going to act as the appropriate power of the Frobenius map on K of n. This is, again, I already gave you this explicit description of the reciprocity map on the entire extension L. This is a finite degree sub-extension, and so again, this is just kind of passing to the, this is just the image, this is just the image of the description that I just gave you inside the quotient group. Okay. And again, the reciprocity map is compatible with this restriction. Okay, so we have that. And so this, again, you see the explicitness. This is really a this is such an explicit description of what the reciprocity map is that I can see right away what its kernel is. Okay, so if it has, again, these guys are linearly disjoint. So if this automorphism is going to be trivial, it's trivial if and only if this guy is the identity and this guy is the identity. So what does that mean? For this guy to be the identity for all units, then again, we talked about this, the kernel of this map here is going to be the nth higher unit group. Okay. So remember the theta overall theta was giving an isomorphism from the automorphism group of K pi over K into the unit group of R, but then we went down to level n, it was giving us an isomorphism on the level n guys. And so we talked about before, so the kernel, the things which act trivially at level n, that almost by definition was the nth higher unit group. Okay. So the kernel, this guy is trivial if and only if theta, if and only if U and U inverse, hence also U, is congruent to 1 modulo pi to the n. Okay, that's what the nth higher unit group is. When is this one trivial? Well, Km is a degree m cyclic extension of K generated by F. Okay, and so when is F to the A trivial? It's trivial if and only if A is a multiple of M, because the Frobenius map is the canonical generator of that degree extension and it has order M. So I'm wondering when this is trivial. It's trivial if and only if A is a multiple of the order of the Frobenius map. Okay, and so that's great. That says that the kernel is by definition the subgroup which is generated by the nth higher unit group and the nth powers of the Frobenius map, and that is exactly the subgroup VMN. Okay, so that was the clever part. It was really, our description of the reciprocity map using Lubin-Tate stuff is so explicit that we can see exactly what its kernel is. Okay, so that's nice. So on the one hand, the kernel is exactly what we say it is because we have such an explicit description. On the other hand, by the general formalism of local class field theory, the kernel of the reciprocity map is always the norms. And so therefore, so by specific stuff, the kernel is VMN. By general stuff, the kernel is the norm. And okay, therefore VMN is the norm from this particular finite abelian sub-extension of L. Okay, so therefore, I found that my subgroup VMN is the norm subgroup from a sub-extension of L. And then I'll remind you about lecture 18, page 5, the way the Galois correspondence with the norm subgroups works. So that's here. If you have a finite abelian extension, then the reciprocity map induces a Galois correspondence between open subgroups of K star that are bigger than the norm subgroup of your finite abelian extension and small and intermediate finite abelian extensions. Okay, so when you have a norm subgroup, that's the norm subgroup of a certain, a certain abelian extension, and then every larger open subgroup, the larger open subgroups are precisely the norm subgroups of the smaller extensions. Well, that's perfect, because if you look back at what we did, we took an arbitrary group H, and H, so H is in between this norm subgroup of EMN and K star. So by the Galois correspondence that I just told you, therefore H is the norm subgroup of some extension, sub-extension of EMN. Yeah, so therefore H is the norms from some sub-extension of EMN, and that's what I wanted to prove. Okay. So I proved the existence theorem there. I proved that every open finite index subgroup is the norm from an abelian extension, but I actually proved more. I proved that it wasn't just the norm of any old finite abelian extension. I proved that every open finite index subgroup was the norm of a finite sub-extension of this abelian extension. And again, now I will explain to you, it won't be hard, that forces this abelian extension to be the maximal abelian extension. So let's see why. It's kind of the same argument. Oh yeah, so here, just writing down, I said this, you see right away that the intersection of this family VMN is of open subgroups is equal to 1. So if each one of those is a norm subgroup, then I have sufficiently many norm subgroups so that the intersection is trivial. Why is that important? Because the kernel of this reciprocity map, when you define it this way, clearly, visibly, in fact, the kernel of this first map is the intersection of all the norm subgroups. That's just what those are just the maps that map trivially in this inverse limit. And just by looking at these VM of n's, that shows that the intersection of all the norm subgroups is trivial. Therefore, this map here is an injection. This map here is an isomorphism. So the reciprocity map, by what we said before, gives an injection from K star into the Galois group. It's the type of injection, so that it's a continuous injection that maps onto every finite quotient. And so if you, as we talked about before, if you just pass to the profinite completion, then indeed the reciprocity map induces an isomorphism from the profinite completion of K star. Again, you choose a uniformizer, that's just the unit group cross Z hat. The only thing the profinite completion is doing here is taking the Z, K star is R cross Z, and it's taking it to R cross Z hat. Okay, so that's local class field theory as promised, but we get more, but wait, there's more. In fact, L is the maximal abelian extension of K. Why is that? It's for very similar reasons. If I take any finite abelian extension, as we showed before, the norms are an open finite index subgroup of K star. And by what we just showed, every open finite index of K star contains the norms of this particular subgroup. And you look back, I guess we don't need to look back because we just looked back at that Galois correspondence. And if you look back at the Galois correspondence, well then for any finite abelian extension, the norms from that extension are a bigger subgroup than the norms from this cofinal system inside my Lubin-Tate extension L. And by the Galois correspondence, if the norms are bigger than the norms, then the extension, it flips, it's a Galois correspondence. The M is contained in EMN, which of course is contained in L. And this tells you that every finite abelian extension is contained in the compositum of the Lubin-Tate extension, K pi, with the maximal ramified extension. And therefore, indeed, we did it. We constructed the maximal abelian extension. Okay, so again, it's not just that we have a formalism. In a rather explicit way, we are telling you what the maximal and ramified abelian extension is. And so the last thing I'll do today, I have one more page, And I will nail this down in the simplest possible case, which is when K is equal to QP. And you'll see it gets really explicit now. So what's the advantage of K being QP? Well, on the one hand, I have a favorite uniformizer over QP. It's just P. And now let me take x plus 1 to the p minus 1. I said this long ago. I haven't exploited it yet. This is one of my distinguished power series. If you just expand the binomial, it certainly starts, it has no constant term. The ones cancel, and then the linear term is x, and then you have higher order terms. On the other hand, if you reduce this mod p, then x plus 1 to the p mod p is x to the p plus 1 to the p. So this thing is certainly going to be congruent to x to the p mod p. So this is a lovely example of my one variable power series from which I can build a Lubin-Tate formal group law. As I mentioned before I even started talking about Lubin-Tate stuff, just as a purely easy exercise involving formal groups, if you take the multiplicative group as your formal group over anything, over any ring R, then it's very easy to work out what multiplication by p is on the formal multiplicative group. And I told you multiplication by n on the formal multiplicative group is x plus 1 all to the n minus 1. You prove that by induction. Okay, so I think that should be an exercise. I think I stated it as an exercise. And so what does that tell me? That tells me that this auxiliary f is multiplication by p. In particular, it is an endomorphism of this formal group law. If you go back to this very first result, okay, lecture 21, page 3, there are all these nice uniqueness assertions. Here we go. And so I take my one variable formal power series, exclam, there's a unique formal group law FF, which has this such that F is an endomorphism of it. But okay, I gave you a particular F and I said, this F acts as the endomorphism multiplication by P in just the multiplicative group. What do we conclude? By the uniqueness statement, there's only one two variable power series for which that holds. And therefore, by the uniqueness in this particular case, this fancy Lubin-Tate formal group law associated, that should be an F, associated to this polynomial F is just the multiplicative group. Well, that's great, because we certainly know what the torsion is, and we know, okay, so now if we plug in the separable points, we're over QP, which is characteristic 0. So separable closure is the algebraic closure. So what are we doing? We're plugging in the points here, and as I told you before, just as by formal group stuff, what is the group that you get when you plug in the elements of the maximal ideal? When your formal group is the multiplicative group, you just get 1 plus m, okay, the first higher unit group here, endowed. And what's the group law? In this case, because the formal group is the multiplicative group, this is also an exercise, but it's just a formal group exercise. The group law is just standard multiplication. What does that mean? Well, we're looking for like pi to the n power torsion, but pi is p, so we're looking for p to the n torsion. We're looking at p to the n torsion just in this multiplicative group. Well, torsion in a multiplicative group means roots of unity. And so therefore, what is this level n guy, this guy obtained by joining the n torsion points over the algebraic closure? It's nothing fancy. It's literally just the p to the nth roots of unity in the algebraic closure. These are the guys in this group that when you apply pi n times, you get 0. But when you apply pi here, it's literally just raising it to the pth power. Okay, so these are the guys that, and again, it's the multiplicative group, so the identity element is 1. And so therefore, the level n torsion guy, which looked kind of fancy in general, is literally just the p to the nth roots of unity in the algebraic closure, which indeed is a totally ramified extension. Okay, you see that in number 32. And the full torsion subgroup is the group of all pth roots of unity, p power roots of unity. And so therefore, what are these Lubin-Tate extensions? The level n Lubin-Tate extension is just QP adjoin a primitive p to the nth root of unity. The maximal ramified extension, we don't need Lubin-Tate theory to tell us this, we just need number theory 2 to tell us this. The maximal ramified extension in general corresponds to taking the maximal separable extension of the residue field. The residue field is a finite field, it's perfect, and the algebraic closure of a finite field is obtained by throwing in all roots of unity. And so the maximum ramified extension is, again, by number theory 2, is precisely obtained by adjoining all roots of unity of prime to the residue characteristic. So K on RAM is attained by adjoining roots of unity of order prime to P, and the Lubin-Tate guys are obtained by adjoining roots of unity of P power order. Conclusion, the local Kronecker-Weber theorem, the maximal abelian extension of QP is therefore the cyclotomic extension of QP obtained by adjoining all the roots of unity. And again, it splits into a totally ramified part and an unramified part. The unramified part is generated by those roots of unity. And then you have the totally ramified part, which is obtained by adjoining the P power roots of unity. And just as an exercise here, I was kind of pushing this R linear action of the automorphism group of Kp over K on the torsion points as being some kind of analog of the cyclotomic character, which gave us the explicit class field theory over Q. I guess we haven't technically gotten to that yet, but it does. The exercise is to show that in this case, this character, well, this character now has values in the unit group, which is ZP cross. You literally can identify this character with the p-adic cyclotomic character in this case. And so this Lubin-Tate theory, among other things, really just reduces to the cyclotomic character in the case of cubic. All right, so that's what I wanted to say about local class field theory. That completes my discussion of Lubin-Tate local class field theory. The last thing we did was we proved the existence theorem, and so that completes the discussion of local class field theory altogether. But as you see, I guess I'll flip back. It really is much more than just the standard formalism of that class field theory is giving you. Why? Because of this result, because this theorem really is telling you much more explicitly what the reciprocity map is actually doing. You always know what the reciprocity map is doing on, the question is always, what does the reciprocity map do on an element of the unit group, right? The ones that are powers of a uniformizer are corresponding to just the maximal unramified extension. So the matter of it is, what does the reciprocity map do? What does the reciprocity map applied to a unit do on the ramified extensions? And it's a little bit complicated in general, but it's really, really, really explicit. It's saying that if you apply the reciprocity map at a unit, it pointwise fixes the maximal unramified extension. Okay, that we think we knew already, at least in characteristic 0. And how does it act on a complementary piece? Well, it acts as the inverse of the way the Lubin-Tate anyway, so the Lubin-Tate theory is explaining exactly what the reciprocity map of a unit is doing. So it really is, and I just gave you a case where if K is equal to QP, then it really is just acting like the cyclotomic character. But in general, it's a little bit more complicated, but this is very explicit. This is actually telling you what this map is doing in terms of explicit formal power series that you could write down if you were so inclined. Okay, so anyway, I'm very happy with this. Like to me, like this, I feel like Lubin-Tate's approach to local class field theory is adds about as much to local class field theory as local class theory already had. I feel it's like twice as good as like standard local class field. Okay, if there are no further questions, I'm sure you'll want to think about all that stuff that I just said. I think in the next lecture, we're going to start talking about global class field theory. So and I haven't thought about it all, but presumably there's going to be a lot of Adels and stuff. And so maybe I really haven't even cracked that chapter of Harari, but what do you bet the next lecture will be? A review of Adels and Adel class groups and things like that. Okay, that was Lubin-Tate class field theory. Yay, see you.